Alright, so we're going to use some calculus in AP Physics C in order to define some of our variables. The most important thing for you to recognize is that the slope is simply a derivative. So the fancy name for slope is derivative. Now we're going to start by looking at a position time graph where the function is a nice linear function. So the equation would be x equals some slope times time. And that would be some sort of constant value. And now in this case specifically, the slope of a position time graph is velocity. Now if we were to split up this position time graph into equal time intervals, maybe call them A, B, C, D, each one of these little time intervals we could find the slope of that segment. And then we could graph those slopes onto a velocity time graph. So if I mark my times A, B, C, and D, and then I find the slope of each one of those little time intervals, each one of those has the same slope. So when I graph it on my velocity time graph, I'll get a nice constant velocity. And notice that I'm trying to put my dots in the mid-time. Remember, an average velocity is that slope using delta y over delta x, and that occurs at the mid-time. Okay? An average velocity always occurs at mid-time. Now let's take another position time graph where maybe it's not as straightforward. So this one, finding the slope would be really difficult. We could find the slope of a tangent line, but finding the slope, or the slope between 2 points to get an average velocity. But to find the instantaneous velocity, or the velocity of the object at any particular time, is really tricky. So let's say this is x is proportional to or equal to t squared. And now if I were to find the instantaneous velocity, I would have to find the slope of a tangent line at each particular time. So those little red tangent lines there. Okay. So if I were to create a velocity time graph to accompany this function, it would be a nice linear function because I've picked a parabola and each point is the same increment change. So each slope is greater than the previous slope by a constant amount. And that sounds crazy. So then we get v is equal to slope times t. And remember, that slope value for a velocity time graph is the acceleration. So now we can get these equations. Now finding out what is the slope of that line depends on the position time function. So I'm going to jump some calculus for you here. So for those of you that haven't had it yet, here's a crash course. For those of you that have had it, you'll get a review. Let's look at a position time function. X of t is equal to t squared. So the one I've done the picture of. So our velocity with respect to time is the slope of, or the derivative of, the position time function. And since it's a change, a delta x over delta t, we call it a dx dt. Now the answer is 2t. Now how do we get to that? we use a general formula, a general function formula for taking a derivative. So if x to the t is equal to t to the n, then the derivative function would be n times t to the n minus 1. So let's look at a couple of examples. Position with respect to time for 3t squared plus 2t. Okay, so to take the derivative, and again, a lot of times we write it as a d dt. The d stands for delta. It's the shortcut for delta. And the t means that it's with respect to t. So the first function would be 6t. That's 3 times 2. So you bring that 2 down, multiply it by the coefficient, that gives us 6. And then t is known as like t to the 1. So 2 times 1 is 2. T to the 1 less power is t to the 0, and t to the 0 is 1. So a lot of times you would see this written as 6t plus 2, and that's it. That is your velocity with respect to time function. So the notation you may see is a d dt of x, and that means that you're about to take the derivative of the position function with respect to time. Now, the slope of a velocity time graph is acceleration. So if we have a changing velocity, let's say that our velocity is, we'll use the same function, 6t plus 2. So d dt of our velocity function would be equal to, now we're going to take the derivative of each piece, so that would be t to the 1, and 1 times 6 is 6, and then it's a t to the 0 beside the 2, and 0 times 2 is 0, and that gives us our acceleration function. So that truly would be a constant acceleration because it doesn't have a time in there, but that's how we can solve for it. Let's do another one. Position versus time. Let's say we have 3t to the negative 2 minus 2t squared. All right, so if we find the velocity, we have to take the derivative, so d dt of that position function. First term, negative 2 times 3 is negative 6. So t to the 1 less power would be t to the negative 3. Alright, and then minus 2 times 2 is 4, pardon me. To the 1 less power, that would be t to the 1. So now we have our velocity function. So we've taken the derivative of the position function to find the velocity function. We could actually graph that. Alright, so the acceleration would be d dt of the velocity function. So negative 3 times negative 6 gives us positive 18. T to the 1 less power will be t to the negative 4. Remember, t to the 1, so 1 times negative 4 would just be negative 4. And now we have an acceleration function with respect to time. You could find the velocity at any particular time or the acceleration at any particular time by substituting the time in there. Now, we can also go backwards. If we have a velocity time graph, we should be able to solve for the change in position. So we can find the area under that velocity time graph, and that gives us our change in position. And finding the area under that nice straight line is pretty easy. Just like a 1/2 base time height type thing. And we call the fancy name for the area under the graph as the integral. Sometimes you might hear it called the underderivative, but hopefully you'll just hear the word integral. All right, so we've got to do the opposite. Of taking a derivative. So let's look at 2 times t naught to t. We need to define our integration. So our position with respect to time is the sum. So that's, think of that little bracket as being a fancy S that's stretched out to mean sum. We're going to add up all the little areas under the velocity time graph. So all those little areas under the velocity time graph. So the integral of the velocity function with respect to time will give us our position function. And if we have our limits defined, we'll have a definite integral and we'll be able to find exactly the change in position. All right, so let's take, for example, we've got a velocity time velocity time function. And let's say that it is t to the n. We're going to set up the general function here. And we'll use c as the constant in front. So, that would be like 2t to the 4 or something. So the integral of t to the n dt, where n is your exponent there and c is a constant. Take t into the add 1. Remember, we're doing the opposite of taking a derivative, so we've got to undo it. Divided by c. So if you look, we can go back up here to one of these functions and see if we go backwards, if we get the same answer. So let's start with our velocity function of 6t plus 2. Remember, that's like 2t to the 0. So our position function would be the integral of 6t plus 2t to the 0. Remember, that's still understood. dt. All right, so we're going to do each term separately. T to the 1 greater power should be t to the 2 divided by 6. That would be t to the 1 divided by 2. That's not right. I've made a mistake. Let me fix this. Up here, my definition, I made a boo-boo. I should have c. So that's going to be a 1 there. Okay. Sorry. Go back up here. Fix this up before you go on. Oops. So it should be c t to the n plus 1 over n plus 1. There you go. That's right. So we'll try one of those again. So that gives you 3t squared plus 2t. And that should be our position function that we started with earlier up here. All right, let's do another example. X of t is equal to 3t squared plus 2t. All right, so our velocity function in this example is 6t cubed minus 4t squared. Okay, so your position function with respect to time is the integral of our velocity function, that is 6t cubed minus 4t squared dt. Okay, so now we're going to add 1 to the exponent, so that's 6t to the 4 over n plus 1, so that would be 4, minus 4t to the 3 over 3. And that is our position function. Now you could find the exact position of an object by substituting in time. You can find the change in position by substituting in the time and finding the difference in the two answers. And that's called a definite integral. So right now what we found is the change in position from 0 or from like 0 to 2 seconds. So if you want to find the change in position, let's say for example 4t squared, your position function would be the integral from 0 to 2. So we write our limits on that scripty s, where the beginning limit is notated on the bottom and the ending is on the top. So it's 4t squared dt. Alright, so then 4t to the 1 greater power divided by the exponent, so 3. And we're going to evaluate it between 0 and 2. And this is how we write the evaluation symbol. So now we're going to evaluate it. Remember, delta x means final minus initial. So we'll substitute in our final time. So 4t cubed with 2 substituted in. So 2 times 2 cubed, divided by 3, minus 4 times 0 cubed, but that's just 0, divided by 3. And that will give us 4 times 8 divided by 3 minus 0. And then, so 32 divided by 3. And leave it in a fraction form or simplify it. And in this case, it would be meters because we were looking for a position function, and we assume SI units unless otherwise noted. So that's pretty much it.